I'm going to begin. Hopefully you guys are getting this out there in Grandview real soon. As I was just saying to Nate here, this is actually something that engineers actually do know about. I've talked to an engineer friend of mine, and he actually sent me a big document. It's about 45 pages thick that explains sort of all the formulas and coefficients of friction and all that stuff, and it was way over my head. But they actually do consider this stuff when they're building roads and bridges. So let's begin. Yeah, how tight to make the corner, how much banking to put on the corners and stuff like that. Yep. So that's what we're going to be looking at today. So the net force on a car traveling around a curve is the centripetal force, which is Fc is equal to mv squared over r. We've looked at that. Okay. And it's directed toward the center of the curve. For a level curve, the centripetal force will be supplied by the friction force between the tires and the roadway. So as you go around a level curve, say for example, even just like driving in town, right? As you go make that left turn, or even on those roundabouts in Europe, it's friction that supplies the centripetal force. Don't know, man. Okay, so as I was saying, on a level curve, as you go around that roundabout in Glasgow, it is friction that actually pushes you around the corner, right? If there was no friction, if it was very icy, you would go around. Maybe that's one reason why we don't have those in Canada. I don't know. I haven't thought of that until just now. Yeah, but they're tiny. There's one out by my in-laws, and it's actually pretty good, but it's pretty tiny. Interesting. A banked curve can supply the centripetal force by the normal force and the weight without relying on friction. So if you're a race car, if you're a racing fan, you will know that when they run the Indy 500, those curves are banked. How come? Otherwise, they'll just slide right off because friction's not enough. They actually have to use the normal force to supply a force to provide that centripetal force. So it's actually gravity that's helping them go so fast. Okay, so first of all, we're going to talk about level curves. So on a level curve, and you guys have this, right? You don't have to draw any picture. So on a level curve, here you have a bird's eye view of the car, and it is the centripetal force, which is towards the center, that is supplied by the friction force. Okay? Now, if you sort of look at another view from behind the vehicle, we have the weight force as mass times gravity. We have the normal force, which is up, Fn, and we have our centripetal force towards the center. What causes the friction force? You remember mu equals Ff over Fn. The normal force is provided by the mass of the car. Fc is the centripetal force here, which is equal to friction force. It's that idea of inertia is trying to get you to go out like this as you go around the curve, right? Inertia is trying to get you to go in a straight line, and friction saying no, and it's pushing you towards the center. Okay? So that's why they throw gravel down on roads to increase the coefficient of friction. So here's an example. What must be the coefficient of friction between the tires and the level roadway to allow a car to make a curve of radius 350 meters at a speed of 80 kilometers an hour? So do you guys have this question right there? Do you have space for it to complete? Maybe on the next page? I always forget. No? 350, 80, oops. No, you don't. Well, you can squeeze it in or throw it on loose leaf. I'm surprised that I don't have that in there. For a level curve, the force of friction is the only horizontal force on a car. And the answer is, I already did it for you. Oh, excellent, even better. For a level curve, the force of friction is the only horizontal force on a car and provides the centripetal force. This can be seen from the free body diagram, this one up top here. Okay, so what I got to do is go to the next page, right? Here we go. Okay, so what do you have to do? The net force must be horizontal, pointing towards the center of the circle. Only the friction force is able to provide it. The normal force and the weight force simply cancel each other out. Calculations are easy if the speed is expressed in meters per second. So the first step is to divide by 3.6 to get you 22.2. And now we're going to calculate the necessary centripetal force. And you guys actually have the answer, or so do I? Do you have something in here? Yes. You guys do and I don't. That seems wrong. That seems wrong. Haven't we been talking about centripetal force the whole time, Nate? Oh. Sam, pay attention. Fc is equal to m. The velocity is that 22.2 squared, and it's all over the radius of the curve is 350. And you notice that you get a value of 1.41 m. Why is it just m? Because we don't know the mass of the vehicle. Right? Can we do it without the mass of the vehicle? Should it matter? Like if Billy's driving his great big what are you driving? Semi. Okay, well he'll drive his semi, and I'm going to drive my little Ford Focus. Should it matter? Should he get more friction than me? Yeah. No. So the mass actually doesn't matter. So when you go like that, if you've got the normal force, which is equivalent to the weight force, which is mass times gravity, so we're going to have 9.8 m. Okay, so this is one of those questions where you don't know the mass of the car. For this flat curve, the centripetal force is supplied by the friction force Ff. Ff is mu Fn. Fn we know is 9.8 m, so we're going to have mu times 9.8 m. You guys must have something else in there. What was the actual question? What is the coefficient of friction? Right. So we're solving for mu. So now we've got an equation here with two unknowns. We've got a mu and an m in there. But we know that our friction force has to be supplied by, or it supplies the centripetal force. And so this mu 9.8 m is equal to the 1.41 m. And what happens to the m's? They cancel. And they should, right? The mass of Billy's semi should not matter. And so you get a mu value of 0.141. Okay? It's, yeah, no, 1.41 divided by 9.8. Now, is this a small mu value, 0.141? Pretty small, right? When we did the wood coefficient one, you should have got a value of about 0.2, 0.25 or so. So like, you know, a sheet of plywood and 2x4 has greater friction than this particular necessary roadway. So what does that mean? It means that anybody can drive around this corner at least 80 kilometers an hour. What happens if they go faster? They might, right? But I mean, really, this mu value is pretty small. So if we put like a bigger value, if we put 30 in there, right? This is the required coefficient of friction. It is not the actual coefficient. This is how rough the road has to be so you can make the turn doing 80. You'll start to slide out. Your rear end tends to slide out, right? Oh, you mean like up on one wheel? Yeah, I suppose, yeah. Like on Dukes of Hazzard. I watched that as a kid. It was awesome. Okay, so it says here, of course, any coefficient of friction greater than 0.141 will keep the car from slipping. This is the minimum value for mu. Notice that the force of friction is perpendicular to the velocity, but it is still in the direction necessary to oppose the motion that would occur without friction. The car will slide away from the center, in other words, to the right in this diagram, if it encounters a patch of low friction surface like ice or oil. Therefore, the friction force is directed toward the center. Notice, too, that we are dealing actually with static friction. The piece of the tire in contact with the road is momentarily at rest with respect to the road. The force of static friction is somewhat greater than the force provided by kinetic friction if the tires start to skid. There are places, if you think about going through the park, when you're coming through the park, there's that one little spot there. The speed limit is 80, but there's a spot there where it's 70, right? Do you know why? It's been 70 for as long as I've been going through the park. No, not that part. There's a part just as you're going down a hill, and then it makes a turn. I think even at the bottom of that big hill, isn't that dropped to 70? I don't remember where it is. It's on a single lane. It goes to 70. It doesn't stay 70 very long. It's just basically around a corner. There are times if you're going to Winnipeg on Highway 6, there's a couple places there around Warren where it drops down to 90. Why is that? It's because the curve of the road is so sharp that you actually have to slow down to 90 because the coefficient of friction isn't enough to hold you there. You have to slow down. Now, that's just recommended. Do people do it at 100? Yep. But if it's a little bit icy or if you've got bad tires, because this coefficient is also dependent upon your tires, right? If you got lousy tires, the coefficient of friction between your tires and the road is actually going to be less. Okay? Okay, so I would like you to try this example. Do you want to try it on your own or should I do it? Me do it? Okay. So here, what is the maximum speed that a 1,500 kilogram car can round a level curve? If the radius of the curve is 100 meters, that's pretty tight. And the frictional coefficient is 0.65. That's a pretty rough road. So we are looking for the velocity. Billy, put the phone down and pay attention. The cows can live without you. Oh, it's not the cows texting you? Oh, your mom then. No? Alrighty, let me grab my notes here because I always mess these up. Uh-huh. I write the physics exam? No, I'll make a mistake for sure. Okay, so the key word here for you is level curve because we're going to do bank curves right away and the steps are different. So when it's a level curve, that means that the frictional force is providing the centripetal force. Okay, Mitch, I'm begging you, pay attention, man. Don't want to explain this 3 times. Nate, don't talk, listen to me. Okay, what makes up our friction force? It's equal to mu Fn. All I've done there is I've taken our old friend mu equals Ff over Fn, and I've rearranged it for Ff. That's all I've done there. Right? So the centripetal force is equal to the friction force, and that's mu Fn. In this case here, we know the mass of the car. Our mu value is 0.65. Fn is m times g. So that's, hey? And it's flat. So it's 1,500 times 9.8, and you get 95.55 is what I get. So that's how much friction force we need to take this 1,500 kilogram car around this corner. We need 95.55 newtons of force. So will friction do it? Cool. Fn is equal to Fw, which is mass times gravity. Good enough question. I sort of skipped a step there. Yeah, that's a big question. Okay, so this friction force has to be equal to the Fc, which is mv squared over r. Right? So if I need 95.55 newtons of force, and I have a 1,500 kilogram car, what velocity can I use on my curve that has a radius of 100? Start flipping stuff around. We're going to multiply both sides by 100. And then we're going to do what? Divide by 1,500. And that's going to give me v squared. I got the answer. I get 25.2. Gotta square root it. You better not be doing 637 meters per second around a corner. You'll get a ticket and probably thrown in jail. Yeah, if you survive, exactly. 25.2 meters per second. Now, of course, we don't really know what that means. So we're going to multiply by 3.6, and you get because that's what people drive their cars in. So if Josh's dad's department has this highway curve where the coefficient of friction is 0.65 and the radius of the curve is only 100, are they going to post a sign saying go 90? Probably 60 would be my guess. I don't know what that error range is, but I'm pretty sure that they drop it considerably. And try it, just keep going as fast as they can. No, I'm pretty sure they don't do that. Yeah. I don't know how much. I'm thinking they would make that at least 70, if not. What makes this so such a tough curve is what? Radius of the curve is only 100. That's pretty tiny. Yeah. You're doing a 90 degree. You're going 90 degrees. You're going from there to there, and then this distance here is only 100. Kind of tough to visualize, but okay. So what can they do to make this road safer? Increase the radius, stretch it out. They'd have to start the turn a little earlier, right? So they have to go buy some land from farmers or whatever, however they do that. Or they can bank it too, right? They do. They pretty much take. They did this. You guys are too young to remember, but when I first moved to town, when you went past the, you can still see the old road. When you go past the golf course there, towards Oak River, as you just get to the golf course turnoff, you'll notice that there's a road that sort of runs closer to the lake. That was the old highway, and it was pretty. You had to slow down quite a bit. It was pretty sharp, and so they've taken it away from the lake, probably because of flooding and stuff as well. They've taken it away from the lake, and I think they've actually banked it as well. If you look at highway corners, you will see that a lot of them are actually banked as well. Some aren't. Like I know that one around Warren there is pretty flat, but some of them are banked. The one at St. Rose, I think, is banked. Okay, so that's the two things they can do. They can increase the radius, or they can bank them. Am I good to go on here? Why do people say semi? Okay, so let's look at a bank curve. I always get this messed up. Okay. So, civil engineers generally bank curves on roads in such a manner that a car going around the curve, Nate, I'm moving on. Yeah, I yell at him all the time too. Yes, I do. Bill, be quiet. See? Civil engineers generally bank curves on roads in such a manner that a car going around the curve at a recommended speed does not have to rely on friction between its tires and the road surface in order around the curve. Suppose that the radius of curvature of a given curve is 60 meters, so it's quite tight, and that the recommended speed is only 40. At what angle should the curve be banked? So here is a prime example of what an engineer might do. This is actually quite complicated, and I wish I had spent some time last night relearning this prior to standing in front of you once again. So here we go. So think about, here's the back of the car, here's the taillights. Okay, you're looking at the back of the car. Okay, you guys, you really got to focus here. Okay, and I need to focus too. Please bear with me for a few minutes. M times G is straight down. Now this is Fn right here. Is the Fn equal to the mg? No. If this was a frictionless surface, the car would do what? It would slide down the ramp. We don't want that. Right? So in fact, the car actually has to be at some sort of speed, or there has to be some sort of friction, so that it doesn't slide down the ramp. Okay? So this right here, this little diagram over here on the right, this is Fn, and you've got F sine theta and F cos theta as well. So that is, this here is this triangle in there. Okay, it's a blow up. Okay? And it's similar to, and you guys know what similar to I think means in geometry sense, similar to that one down there. So consider a car mass m going around the curve. The car's weight mg acts vertically downward. The road surface exerts an upward normal reaction force F on the car. The vertical component of the reaction must balance the downward weight of the car. So F cos theta is equal to mg. So think about this diagram right here. This theta right here on the ramp is equivalent to that theta there, right? You guys know that, I think. This theta right here is equivalent to this little guy in here. Okay? this F cos theta is up, and it has to be balanced by the weight force, M times G. So in other words, F cos theta is equal to mg. That's where that comes from. Are you with me? The horizontal component of the reaction, F sine theta, acts towards the center of the curvature of the road. This component provides the force towards the center of the curvature, which the car experiences as it rounds the curve. In other words, so this guy right here, this F sine theta, becomes the centripetal force because it's directed which way? Towards the center. F cos theta is up, F sine theta is towards the center. That's our centripetal force. And here's the part where I always mess up, so back to the notes. Okay, you guys have space here, right? Yes? Okay. So, since from the diagram, we've got, in other words, right here, you should have F sine theta is equal to mv squared over r. The F sine theta from that diagram above is equal to the centripetal force. Yeah? Okay. Now, if you look at this diagram right here, remember trig identities, pre-calc? People? Guess what? It's going to come up. The tangent of theta, do you guys know what the tan trig identity is? That's because it's opposite over adjacent, right? It's the easiest one, right? So tan theta is equal to F sine theta over F cos theta. Yeah, we heard you, Nate. Pay attention to this now so you get it later. Tan theta is equal to F sine theta over F cos theta. And I'm going to rearrange that. I'm going to bring the F cos theta up here. And I'm going to write, and I'm going to flip them around. So I'm going to bring the F cos theta up here to the left. I'm going to flip the left to the right. I'm going to write F sine theta is equal to F cos theta tan theta. Okay? So all I did there was bring the F cos theta up to the left. I got F cos theta tan theta equals F sine theta, and then I just flipped them so that I got my F sine theta on the left. Okay. Now, F sine theta we've already said is equal to mv squared over r. I'm going to run out of room. mv squared over r from before. F cos theta is equal to, from before, where is it? mg. You getting a sense of what's going to happen here? Nate? It's equal to mg because F cos theta must be balanced by Fw, which is mg. You should recognize what's about to happen. Because the mass of Billy's semi doesn't matter, or my scooter. You have a scooter? I do not. You have to wear a helmet? I don't do that activity, so. Probably, yeah. Okay, so I'm going to get v squared over r is equal to g tan theta. Now what we want to know is the bank, right? The theta. So we usually write this formula like this. We usually write, tan theta is equal to v squared over rg. We take the g down there. This is the formula that you use to determine what angle your curve should be banked at. This is the formula derivation, once again. I know. Yeah, I know. I should have told you ahead of time, but sometimes it's good to be a little scared and then relieved. I'm expanding your brain, Nate. That's what I do. I'm a brain expander. I think that's how I'm going to introduce myself. You know, what do you do? I'm not going to say I'm a teacher. I'm a brain expander. Sam's smiling at me. Note that if the car attempts to round the curve at the wrong speed and the difference has to be made up by a sideways friction force exerted by the car's tires and the road surface, unfortunately this does not always work, especially if the road surface is wet. So this will get you safely around the curve with zero friction. What's providing the centripetal force? Where's the overall fundamental force that's providing that centripetal force? Gravity. Gravity and the fact that it's banked. Okay? Are roads, excuse me, are roads frictionless surfaces? No, of course not. Okay? Could you round this at greater than 40 kilometers an hour? Absolutely, because friction would be involved in there. For us to do bank curves with friction is like crazy. So we're going to be doing frictionless bank curves. Okay. I think I can go to the next page. What do you guys got on the next page? Another sample, I think, right? Oh, yes. Here we go. Example number 9. Oh, I think it was on, yeah, that's right. The two samples are on the same page.
No, it's actually weird. It's back.
Yeah, I know. Billy. Mitch. I'm going to do this, and then I'll give you some time to work. So we got a race car traveling along a bank curve at a speed of 120. Doesn't depend on the force of friction to keep on the track, so it's frictionless. If the turn is banked at an angle of 25 degrees in the horizontal, this time we're at, just relax, you guys. Oh my God. It's a good thing I got that certificate that says I can run a daycare, because I do. I have a child care worker level 3 certificate. I'm qualified to be a daycare administrator. Because I'm already working in one, Mustafa. Daycare for teenagers. I'll explain that story in a bit. What is the radius of rotation? So you're going to write, he's a race car. 120 is not that fast. Tan theta is equal to, what was that formula that I just came up with? M. I can't remember it. There you go. V squared over RG. Jeez. V squared over RG. Does the velocity have to be in meters per second?
It already is. 36.3.
Oh, they've changed it for you down here. So you would have to do that. So you would write, Nate, tan 25 is that 33.3 that we got by dividing by 3.6 over here. So that would be a step you'd have to do. You're solving for R, so it'd be R times 9.8. Now, sometimes people have a little trouble with the math here, right? So we're going to cross multiply, that's right. We're going to bring the R up to the left. We're going to bring the tan 25 down. 33.3 squared all over 9.8 tan 25. You do have to be careful when you got more than one thing on the bottom. Use some brackets. Yes, because that's a common mistake. You should get a radius of 243. Tan 25. You're not finding the angle.
You got 242?
240, 42 probably rounds up. 243. Okay, so there is unbanked curves and banked curves. Banked frictionless curves. There are a couple questions in that problem pack that's attached there. I think they're the last couple ones. There are. The ones that say bonus 7 and 8, those are banked curve with a frictional coefficient. I've never had a student figure out the answer.
What?
That is your challenge
Which one?
for questions 7 and 8. I've never had anyone figure it out. They keep asking me for help, and I don't know. I can't get the answer either. So
Well, then maybe the he's wrong.
it could be, but we have not yet. And that is the challenge. I'm waiting for a student that can figure them out.
Okay, I got it.
Okay. Give me 30 seconds, Sava. Okay, so you've got some time to work. You've got banked and unbanked curves. Tomorrow, I think what I'll do is I've got a couple questions from the textbook that I think I'll do.
Oh, there's plenty out here.
Just a couple of samples. Okay, I'm going to give you tomorrow to work as well. Tomorrow's Thursday. Friday, I'm going to do the Flying Pig Lab. I got to figure out a way to get those guys out there watching us. It'll be happening in my classroom, the Flying Pig Lab. It's a sort of a demonstration lab. I only have one flying pig. And after that, I'll be done. So we'll schedule the test for this probably like Wednesday or so kind of thing. That'll give you Thursday and Friday for exam. You guys that are camping next week can write the test when you get back. Basically, all you got to do is write the UCM test sometime next week, and that's it. I am not doing any energy stuff. I don't have time.
Sir, right on. Should I set up my test today, sir?
Yeah.